so we're going to talk about finding the area of a regular polygon using two formulas. Now, in this situation, we're talking about a triangle, and it's an equilateral triangle if I use the word regular. So even if there's subtle errors, I tried to do the best kind of freehanding it with tools, I guess. So that's not really freehanding it, but so we're going to start with the first general rule. Okay, so if I use the traditional formula, I do not have well, I do have a base since it's regular. Therefore, all the sides are the same measures, right? It's an equilateral triangle, so we can fill that information in. Now, what I need to find is the vertical height from here to here. So I left the space here just to put that number in, but that would be like the distance from here to down here, perpendicular. So this is going to be the center of the circle that goes around this triangle. So we're circumscribing the triangle, and this is an important point. You should have learned how to find that point at some point. But so what do we do to do that? So we can think of this triangle, knowing that it's equilateral, in terms of I'm going to just recreate the triangle off to the side as just a kind of general approach, right? So I know that all the angles are 60 degrees, right? And so I can kind of take this information, and I know all the sides are equal because it's a regular polygon. So that means I'm going to drop a line right down the middle, and it splits this into two congruent segments. So if I kind of pull the right segment out, I can kind of see that I have, these would all be 10, right? Of course, centimeters, and 10 centimeters. So I know that this here is 10 centimeters. So it's just taking this and extracting it to go over here, to go over here. So in order to recognize this, I know that this angle is 60 and this is 30. So in order to find, say, this side right here and this side right here, there are two approaches. I can use my, actually there's three approaches. I can use my special right triangle rule for it. And if I do that, I can easily say, all right, well, this is a 30, 60, 90 triangle, and I need to remember the basic ratios of that. It's a 1, 2 square root of 3. So if this is the radius, right, then the short side, which is opposite the shortest angle, is half of that. And then the long side is the short side times the square root of 3. So there are some things that you do need to remember. It's such as the long side is equal to the short side times the square root of 3, and the hypotenuse is equal to 2 times the short side. And you can kind of extract that information from the rule if you pay attention in other videos. So now that we have all of this, we can kind of see that the area of this triangle, if I just use the original formula, I know I have this 10 base here, and then I have the height of 5 square roots of 3. So that total height would be this distance here. So I'm going to just kind of drop an altitude in here. It's going to be perpendicular just because of the nature of the way I set this up, but that would be my altitude. And this height right here is that 5 square roots of 3. I don't want to put it into the shape yet because we're going to get a little complicated. So if I just plug in the information, I can just use this formula, and I get 1/2 times the base, which is 10, right, times the height, which is 5 square roots of 3. And now, once I start doing this, I just have to kind of remember some basic techniques that allow me to just, multiply with a little bit of ease. And so I can just go ahead and say half of 10, which is 5, right? I can divide this, and I get 5 times 5 square roots of 3, which is just 25 square roots of 3. And if you need to kind of look at a calculator, we can say, all right, well, 25 times 3 square roots is 43.3. We can approximate that. So the area would be 43.3 centimeters. And since it's area, squared, right? So now I want to look at this other formula here. So this other formula, the reason why we want to look at it in this situation is because it's going to help us understand larger situations. And there's kind of multiple ways we can kind of do this, but we're just going to look at it one way right now. And so this center point is kind of important. So we see the circle that went around it. So that center, if I was to go from the center to the edge, I'm just going to kind of draw this and kind of connect it so you see. This is what you would consider to be a radius of the circle, because it's from the center of the circle to the edge of the circle. And of course, we should know how to write the equations of circles at this point. But now I have this different triangle here. So if I was to kind of get rid of this little altitude I drew, right? I have this triangle that kind of is in the middle. So if I pull that triangle out, and I'm going to do that right below, and again, I'm not going to use tools for this. I'm going to kind of freehand it. Not great, but that's not really the idea. Isn't to be great, but is to get it as perfect as possible. So these radius actually cut this in half. You have to take my word for it does that. But if you have learned about, say, this is the orthocenter of the altitudes, it's the centroid of the medians, it's the circumcenter for the perpendicular bisectors, and it is also the incenter for the angle bisector. So if you remember all those things, this point on an equilateral triangle is all the same point. But the point behind it is that now I'm going to look at this bigger triangle, and so I need to calculate this big angle, right? But if I did draw back this kind of this line here, I'm just going to draw this one because it's going to be part of it. Now I can kind of see I have these three congruent segments, which is how we determine the central angle. And the central angle we can kind of find simply by saying 360 divided by the number of sides. So there's 3 sides, so 120 degrees would be this angle. Right, that's 120 degrees, this is 120 degrees, it's 120 degrees since a circle makes 360 degrees, and this is kind of a makeshift circle, but it gets the idea. So this is 120 degrees, but I'm going to drop this little line here, and this little line right here, I'm going to draw it in just a different color because that will help it be distinct. I'm going to draw it in orange. This little line right there, that is actually, that little distance is the apothem. So that is also right here. Now notice that this is 120, so we know that this must be 30 and this must be 30 because all three should add up to 180, and it's isosceles since these are both radius, so they must be congruent, right? So I'm going to pull aside just one of the triangles, and I guess I'll pull it off to this side. I'm always going with the right-sided triangle, not sure why. I mean the right triangles, but the one on the right. So this is 8. Now notice that the whole base was 10, which would be this, right? That would be 10, so half of it is 5. And so what I need to find is the distance here, right? I need to find this length here. But notice that this was 120, and I split it into 2 congruent angles. So this is 60, and this is 30, which we already knew was 30 over here. So now I can use my 30, 60, 90 rule to calculate the apothem very easily, right? Because I know that this is the long side, so, and this is the short side, and we kind of went back to these two little scenarios, and I don't have a hypotenuse, so I will figure out that the long side is 5, so I can plug that in to our special right triangles. So the 5 is equal to the short side times the square root of 3, so we simplify and we divide both sides by the square root of 3, and those cancel out. But we do want to rationalize the denominator because sometimes you will be required, that doesn't equal this is multiplying, but sometimes you'll be required to leave things in simplest radical form rather than converting to decimals. But when I do multiply, I get 5 square roots of 3 over the square root of 9, which is 5 square roots of 3 over 3. So that is the value of A, okay? So now that we have 5 square roots of 3 over 3, we know that's the value of A. And so we're going to use the formula for the area of a regular polygon, and we're using it with the equilateral triangle just so we get an introductory understanding of it, but it proves, the first formula proves that we can use this formula and get the same answer. So it's a good use of understanding. So I go back to the area formula with the apothem, and it is 1/2 a times p, and I know a is this value right here, so I can plug in that value. I got 5 square roots of 3 over 3, and that is the a. And then the perimeter, right? I have a perimeter of my original triangle is 10, 10, 10 is 30, right? So it's of course 30 over 1, and now I could multiply everything. I can cross cancel, so I'll just show you that it's going to be 30 times 5 is 150 over the square root of 3, and then 2 times 3 is 6, and so that just simplifies to 25 square roots of 3, which is what we had up here when we used the other formula. So it is 2 techniques to find the area of the entire I'm just shading this in. This would be the whole area. We didn't find the area of this little triangle. What we found was just this little segment right here, this little segment right here, and this segment right here. And using that, we can then calculate with just this formula right here the distance the area of this shape. And so I'm going to go through the area of another one shortly.